So welcome everyone. I guess this is the first OpenXLA meeting of the year, if I'm correct. Yeah, welcome. Next slide. So as we always do, we want to just restate what the mission of OpenXLA is. We'd like to build, as a community, an open state-of-the-art ML compiler ecosystem with our hardware and software partners here today and more to come. And we're really leveraging the best of XLA and MLIR and also Erie. If you remember correctly, we announced before the break that Erie will be joining the OpenXLA project. So we're excited over the next few months to make that happen. Next slide. So as we always do, I think we want to introduce any new attendees. So is there anyone here today that hasn't previously joined an OpenXLA meeting or just hasn't introduced themselves before to the group?
Yeah. I'm Amith. I'm attending the first one today. I'm from Annapurna Labs, AWS.
Oh, excellent. Welcome.
Fahim Shafi with NVIDIA, also joining for the first time.
Excellent. Welcome, Fahim.
Sofiane Yus from ARM, also the first time attending.
Fantastic.
This is Isaac from IBM. This is a first attendance for me.
Oh, excellent. So a new person from IBM. Fantastic.
Hello, I'm Christian. I used to work for AMD until last week, and now I'm at Stability AI. And I'm here actually to give maybe a 2-3 minutes testimonial because we really appreciated the help of like Google, Node.ai in accelerating stable diffusion through Erie and Vulkan. So I don't know exactly when I do that during the hour, but that's why I'm here.
Excellent. Yes, fantastic. And yes, well, I think we have some maybe time at the end. Tayef, that's correct, to maybe do that.
Good. Hello, I'm Luis Murillo. I'm here with Dean Fitzpatrick, and we are both from AMD. Still at AMD and already missing Christian.
Great.
Anyone else?
And this is Brian from NVIDIA too. Sorry, I'm using my own personal account.
No problem. Welcome. All right. I think that's everyone. Okay, so just a brief overview. We like, especially for new folks, to go over kind of our collaboration channels. So we try to have a monthly meeting the third Tuesday of every month at 8 a.m. PT. That's to accommodate our EMEA and APAC attendees as well. We're trying as much as possible to rotate the meeting host and scribe. We haven't been able to do that yet, but I think we're going to be setting up processes to better enable that going forward. And we try to provide the agenda the week before the meeting. And tomorrow we will share meeting minutes, a recording and slides from this presentation for those who can't attend. Our meetings tend to include more technical development updates, design proposals, and also larger community topics like governance and processes and better ways of collaboration, in addition to some business and marketing things that we hope are coming up in the future. Next slide. So these are just the different ways in which we collaborate. So of course, there's the GitHub organization where you can submit design proposals, PRs, RFCs. We have a community repository where we actually currently have a governance proposal for review. And additionally, community discussion channels, technical discussion channels. And we have a Discord that we'd really like you to join. We often post updates and wins for the community in there, as well as any as needed sort of changes and updates to meeting schedules, etc. Next slide. All right, so our presenter for today is Sandeep from Google, and he's going to present on the StableHLO specification. So take it away.
Yeah, thanks, James. Hi everybody, I'm Sandeep Dasgupta, and today I'm going to present our work on StableHLO specification that we developed recently. This is a collaborative work with a sizable contribution from the StableHLO team within Google, which I'm a member of. So I'd like to give a big shout out to the other team members, Eugene, Ganyan, and Shubhankar. So StableHLO is an ML's offset inspired heavily from MHLO and HLO. As the name suggests, it is a stable version of HLO, which extends it with support for versioning and compatibility. By StableHLO specification, we mean a documentation artifact which defines what a program in StableHLO language means. In this presentation, specifically, I will talk about the details, the development process of this specification, that happened over the course of last 2 quarters in 2022, and some of the significant milestones that we achieved along the process. Next slide, please. With StableHLO, we are aiming to create a portability layer between ML frameworks and ML compilers. Having a specification will definitely help the ML frameworks understand what they are targeting to. At the same time, knowing the semantics will help the compilers for code generation. Next slide, please. Some of the goals is that we want the specification to be a reference for StableHLO producers, and also want that to emerge as a single source of truth for various StableHLO consumers. Some of the non-goals that we have for the recent version of the specification that we developed. Some of you know that StableHLO is bootstrapped from MHLO, and the initial goal was to develop the specification of the offset we bootstrapped from, not to augment or customize it in any way. So just I want to note here that there is a separate RFC process to make changes to the offset. And secondly, there are various interesting topics around auto-generation of specification from some other artifact. So we have a future goal to explore similar opportunities, but we didn't pursue anything of that sort in our recent venture. Next slide, please. StableHLO, as I said, that StableHLO is inspired from MHLO and HLO, so it is natural for us to get motivated from the existing specifications of HLO and MHLO. So let's start with the HLO specification. So it has a significant offset coverage. It has a detailed account of input-output types and semantics. There are assistive diagrams for various non-trivial ops like scatter and gather. And occasionally they spell out various interesting ML use cases for curious readers. The link to the specification is at the title of this slide. Next slide, please. Next, we have the specification of MHLO dialect. This is actually auto-generated from MHLO dialect operational definition specification, which is the source of truth. The verification code for each op is either auto-generated from the constraints specified in the ODS, or they are custom developed using C++ method. And the specification of all the ops follow follow the same format. And this is actually a property of MLR ODS itself. Next slide, please. Because we are like so as I said, there is a lot to inspire from HLO and MHLO spec. For example, we should follow a uniform structure. We should leverage the existing verification constraints that we already have from HLO, and also provide assistive diagrams if necessary for clarity. And at the same time, there is a lot of improvement opportunities of these existing specifications with respect to resolving occasional ambiguities, comprehensively specifying constraints, and by introducing formalism. Next slide, please. So we started with defining the specification of the offset we bootstrapped from, which is MHLO. And while defining the specification, we religiously consult these following artifacts. For example, the HLO verifier. These are all there are links to all the artifacts. So first is the HLO verifier, which has constraints for input outputs, the shape inference for constraints related to the shape of the output. HLO evaluator provides us execution semantics. Also, this method HLO instruction create from proto It has a very nice summary of which metadata is supported by which HLO ops. So we review this method to make sure that we are not missing on any metadata. And last but not the least, we were in constant touch with the HLO developers. This is to understand the semantics even better and resolve ambiguities if there are any. Next slide, please. So there are some features of our specification. The syntax is specified using extended BNF. The semantics is defined semi-formally using a mix of natural language and a set of mathematical notations that we defined along the process. Even though we are like fairly close to having a truly formal and self-contained specification, but there is a lot of room to for improvement. For example, tightening the formal notation that we are using. And even with this semi-formal specification, we can have some immediate benefits. For example, we are getting an unambiguous, pretty unambiguous specification, and also this formalization will help tracking discrepancies in verifiers and shape and type inferencers back to the spec document. So yeah, next slide, please. So let's go through an example of a concatenation op. Just for the completeness of the presentation, what concatenation op does is it takes one or more tensors and try to concatenate them along a specific dimension. This excerpt is taken from the HLO specification, and I've highlighted some interesting points from the specification. For example, the point 1 is about the fact that the input operands are variadic. The second point is about talking about the rank of the input and output. So it's actually a constraint on input output. The third point is again a constraint on the output shape. And the fourth point is about it's a constraint on the input. So what I'm trying to say here is that the existing specification for this particular op has a lot of constraint specifiers on input and outputs, but what is missing here is what is definition of what needs to be computed. Just I want to note here that in the full specification, because this is just an excerpt, there is a full specification where HLO has provided 2 examples and a diagram to explain what the computation is involved in the operation. So, but I believe that there is a opportunity to improve this prose in order to make it more specific. So next slide. So this is what we have for StableHLO specification. This is just a part of the specification. So, and I highlighted one interesting part where it says what is being computed in a precise manner. So it's actually says what the result value is as a function of inputs, and all the unknowns like R, D, they are all defined in the specification. So it's not defined here for brevity. Next slide, please. Again, another example of RemainerOp. The specification talks about the sign and the absolute value of the result, but there is some ambiguity on the semantics, whether it is close to F mod or STT remainder. Next slide, please. Yeah, so this is what we have in our StableHLO specification. The highlighted part is what is being computed for integers, for float, and what the behavior of the float operation is. And in the next slide, please. And this is a previous slide. Yeah, so another point that I want to mention is that for this particular op, we also specify that this operation is not exactly equal to what we have in the IEEE standards with respect to the rounding modes. Next slide. So also we follow a structured format of the specification, which has sections like semantics, inputs, outputs, and constraints, and example. For example, next slide, please. So this is a full-fledged specification of an op, the ceiling op. As you can see that there are various sections specified here with the semantics, inputs, output, along with the constraints applied to those input outputs, and the constraint is defined later with an example with some simple example with some inputs and outputs. Next slide. And also in the specification, we make sure that the constraints are specified explicitly. So we have different kinds of constraints for constraints involving input outputs, constraints related to the types of the output. In the next slide, please. So this is just a constraint section of from our specification for a reduced window operation. So as we can see that there are the different kinds of constraints are specified here, and we believe that having a clear split between the verification and a result type constraint will make these constraints readily usable to implementations like verifiers and shape inferencers of StableHLO. Next slide, please. Yeah, the next. So we'll talk about a bit of our future work. So at this point, we we fully support the statically shaped StableHLO offset. But there is a lot else to cover as well. So for example, a number of offsets we already spec'd is around 94, like 79%, but there are some ops related to dynamism quantization that we want to target. Also, as I said, we want to fully formalize the syntax and semantics. And one benefit of that is going to be that it will facilitate introducing dynamism and quantization by adding a small delta over the existing specification. Next slide, please. So also, we are in the process of implementing a readable reference implementation of the specification. In the StableHLO GitHub repository, you can already see that there is a prototype of the implementation that we are working on. Next slide, please. Also, we are in the process of developing a conformance test suite that consumers can plug into and run on their device. So, and we started talking with various groups about this. Feel free to add your thoughts on this GitHub ticket, which I just opened yesterday. Next slide, please. And also, we want to contribute back to the XLA operation semantics, which we benefited from. So, next slide. Yeah, with that, I will conclude my presentation, and thanks for your time.
Excellent. So I think now we want to pause for some brief Q&A, about 5 minutes, and then we actually have a presentation from Amazon. It looks like we actually have some questions in the chat. It looks like from Vinod, does StableHLO dialect use any other dialect, for example, shape dialect? I think that's Sandeep or Eugene.
I think Eugene actually answered in the chat, but
sorry, my bad. Fantastic.
Let me say that verbally as well. So, you know,
Yeah.
as mentioned in the chat, StableHLO's design for dynamism inherits MHLO's design for dynamism. You know, as Sandeep mentioned, we forked MHLO basically when we created StableHLO, and in this current design, dynamic programs, they use multiple dialects to, you know, express their semantics. So MHLO dialect or StableHLO dialect plus shape dialect. And shape dialect is used for several different reasons. One reason is, you know, shape computations, for instance, computing a shape for a broadcast or for a reshape. So these computations are often expressed using shape dialect. And the second reason is verification or like constraints, you know, however you call it. So basically runtime checks that, you know, the actual shapes of operands make sense. So for example, if you add two tensors at runtime, they must have the same shape. So this is someone has to verify that. And we're doing this through shape dialect.
So I guess the question I was leading up to really was that the producer of StableHLO can just use the base dialect without shape information except just saying question mark. And then OpenXLA would have to infer the information about shapes, right? And that's where I think that becomes very specific to the the language you're compiling or the capabilities of XLA. So the question really is that if you're going to use shape dialect eventually to specify the precise semantics, that means OpenXLA has to support everything you can express in shape dialect, right? So the real question is, will you be specifying what shapes are legal and what shapes are not legal in OpenXLA?
Yeah, that's a very good question. So certainly that's a gap at the moment. And, you know, as Sandeep mentioned, this is something that we're planning to address in the future. So the spec not only includes, you know, the currently statically shaped specifications, but also explains how to build dynamic programs comprehensively and like in details elaborates the semantics, including like, you know, whatever other dialects might be needed.
Right. Okay, good. Thanks.
Looks like we have a question from Rich. Can shape specification differ per platform?
So do you mean the constraints from the shapes, or?
Yeah, I'm just trying to get a sense of how do you expect to envision supporting a GPU with, you know, broad flexibility, fixed function ASIC with zero flexibility and stuff in between.
Yeah, so for developing this specification, we actually consulted some platforms, not all. So we have a goal to cross-check or cross-validate this specification over multiple platforms and see we can unify the specification. So right now, this is mostly on the CPU using XLA compiler.
Yeah, I think if you're going to try to make it work for everybody simultaneously, you're going to lowest common denominator is going to be no shape support. No dynamic shape support, right? So, you know, I guess. Go ahead.
Perhaps to answer it in a different way, Rich, I think we already have sort of the question with, you know, we have different hardware that have different amounts of dynamism they support.
Yes.
I think what we're focusing on here is the generic like specification of them, like the ops. You know, we can represent the graph with, for example, dynamic shapes. Now, whether a platform can support it, that is a different question. So now it becomes a question of, you know, do you need to specialize at runtime? Are you able to precompile? You know, and I think sort of at the spec level, I do agree with you. We don't want to focus on the lowest common denominator. I think that will get us in a bad spot.
Right.
If that answers the question.
It does. I mean, I think I tend to agree that, you know, you want your specification to be as robust as it can be to accommodate everything possible, but you know, there certainly is going to be a variable, you know, range of supportability for different platforms. So that has to be, you know, somehow handled. And, you know, it can be done, let's call it runtime. It can be done compile time. It can be done, you know, dialect time, whatever way in which it possibly can be done. I actually think we should be opinionated on that, though, to be honest. I think we should actually have it.
So sorry, I can't find my hand up button on this screen. But I think that there's a couple of points here. One is that that the dynamic shape support in StableHLO is effectively a V0 that you know, we need to elaborate forward. The second point is I think I agree with the point that was just being made, which is that that in practice there are multiple levels of dynamism that certain domain-specific compilers will support, and that's often dictated by it's under reactions. That's also often dictated by, you know, hardware invariants or things that you've put on it and whatnot. So I think that as we move this past V0, we need to define those tiers of dynamism. You know, currently the shape dialect lets you define, you know, kind of fully unranked, very, very wide open dynamism, and we should have a further spec wherever we go that says basically how you can verify that a program is actually more static to that, to some, you know, whether it's ranked dynamism, fully static, you know, broadcast invariant, something. We need to make up those categories, and then StableHLO itself can have compiler passes and whatnot that you know, attempt to legalize the program into those forms with additional constraints. We've taken that approach with TOSA and TF Lite, which have a limited form of dynamism that is not compatible with what the lower level compilers want, and it tends to work out, but it needs specification and a delineation of what targets we're going after. I think that's probably the only way out of the lowest common denominator problem.
Okay. I think Mehdi had his hand up next.
Yeah, thanks. Just to upscale a bit from the dynamism, the general question is like there are aspects of the specification that some hardware or some platform will not be able to support. I think what was discussed at some point was looking into formalizing this in terms of, I don't remember the term, extensions or capabilities. There is precedent with like OpenGL at vendor extensions, or OpenCL. Also, you can query the current platform to know, do I support this kind of thing? Even CUDA, I think, had those kind of thing where like interaction between a texture and other things, where you can query the actual hardware and know, do I support this feature or this extension to the offset? So dynamism could be one, but maybe in the future there are also other aspects of the spec that we can be like this whole group of things. Quantization, you know, do I support, you know, arbitrary bit quantization or 4/8-bit quantization on this current hardware or not? So maybe that would get into this to avoid restricting the spec to the lowest common denominator, but still having some extensibility.
Yeah, I'm a big +1 on you know, having an extension mechanism and a healthy extension community baked into the process of evolution.
I think let's take one last question and then we can move on to Amazon because we want to fit that in as well as some other community news. So maybe Vinod, maybe.
Yeah, I was just asking, is there a time frame for the development of the shape specs? I mean, it seems that even the shape dialect, there will be a number of issues that may not have yet been. I mean, question really is shape dialect adequate for expressing the full semantics you want for StableHLO, right? So if you already started on that, then that puts some constraints. But if it's something in the future, question would be, what's the time frame for that, right?
Yeah, thank you, Vinod. That's a great question. This is something that we are planning to look into in Q1, and we even have a ticket, you know, in the StableHLO repository that you can follow. And in this ticket, there's kind of a rough plan of what we're planning to do. Plus, there I tried to capture a bunch of feedback from various stakeholders in the community who are using MHLO, and they provided feedback about dynamism support. So if you'd like to participate, you know, let's talk about this definitely.
Sure. Yeah, yeah, thanks.
Thanks, and obviously this this invitation to, you know, participate and contribute extends to everyone in the meeting, out in the meeting. So thank you all for your thoughtful feedback.
All right, Amith, are you ready?
Yeah.
Excellent.
Can you hear me?
Yes.
Today I'll just give you an end-to-end our experience with PyTorch XLA on a Trainium cluster, which we released recently. Next slide, please. So I'm from AWS, Annapurna Labs. So just wanted to give you a high-level overview of what I'm going to talk about today. So first, I'll explain the motivation and the high level, like the lowering flow of how the application, you know, starting from the PyTorch level all the way down to the ops level, the XLA ops level. And then I'll talk about the execution flow, how we are doing XLA aware orchestration of the different components, and then our experience optimizing large models, GPT and BERT, you know, some mismatches and gaps, and then our you know, future plans. Next slide, please. Just to introduce, you know, to the broader audience of our Trainium architecture. When you talk about EC2 cluster of a Trainium, the TRN1 that you see there, that's in each instance of Trainium. And if you zoom into each of those instances, what we see is a topology, a mesh topology, where each Trainium device connects to another Trainium device in a two-dimensional mesh. Okay, so you can think of each device comprising of 2 Trainium neuron cores. So in total, what we have is about 32 neuron cores per Trainium instance. Okay, and we are trying to scale it to over ultra large scale, 10,000 plus more clusters, and all of these instances are connected by our own EFA fabric. So right now we support about 800 gigabits per second bandwidth. So this is the overall architecture of the Trainium. So what we want is a system, an end-to-end system that can accelerate very large deep learning workflows with very good performance and scale. So that's our goal. Next slide, please. So I want to just summarize the three main objectives or goals we have. So the first one, as I mentioned, we want to support a large breadth of models spanning multiple domains, not restricting to NLP and vision, but extend even more than that. And we want to, scalability is very, very important. So we want to at least start from 175 billion parameters and then, just scale up. I don't think we have any limits of how much we can scale, but at least start from a huge model space. And we want to ensure that we are getting a very good utilization of our system. So right now we support about 3.36 petaflops of BF16 raw performance per Trainium instance. So we want to utilize this as much as possible. And the ultimate goal that we have also is a seamless transition, so we know that PyTorch natively supports, runs very well on GPU CUDA platforms. So what we want to do is take the same model and support a seamless transition to this new, I would say not new, but a different architecture of XLA with PyTorch. So we want to support a seamless transition. So that's our goal, because it benefits our customers. Next slide, please. So I want to basically just give you a high-level flow here, just to understand how the lowering is being done from PyTorch API all the way to the Neuron API, so the Neuron core. So what happens is when you have your application, and when this application is lowered down, if you take a model, let us say GPT or BERT, or for rather any other model, when you lower it, you generate three types of HLOs. So you have your initialization HLO, and you have a forward backward HLO, and you have optimizer HLO. Okay, so this is how it is partitioned across these three different HLOs. And what we should see here is two workers, worker 0 and worker n. That n stands for any worker in your application. When you distribute your parallelism, right? So it represents any worker, and I want to kind of pair them together, because the lowering kind of is important, because on each of the workers, the way it happens is same but slightly different also, because you could have a different workflow of the code in one worker and different flow of the code in other worker. So I want to kind of pair them together and explain that. So you start from the high level API, and then you go to this PyTorch XLA layer, which converts the PyTorch API into XLA ops. So they can lower to XLA ops. And then what happens from this XLA ops, you actually go into compiler domain, where you have front end and you have back end, and there our Neuron compiler kicks in, and it takes all the HLO ops and compiles them to our Neuron core. Okay, and it also generates both compute and communication operations in the HLO. And what a Neuron core does is it takes these graphs, which have both compute and communicate operations, and it optimizes them simultaneously. So that's very important, because we want to have very fine-grained overlap between our computation and communication operations. And our hardware also is built around that paradigm, that we have separate compute and separate communication engines. And it's important that to utilize your Neuron core efficiently, we need a very good overlap between them. And I also want to raise a point about SPMD and MPMD, because when you have an SPMD graph, that means all Neuron cores see the same code flow. So that helps the compiler optimize it very, very rigorously. And we like SPMD, but the PyTorch XLA doesn't restrict to SPMD. The code can take different paths. Each worker can take different paths as long as they call the communication API at the same time, at the same place, so that there is no deadlocks. Next slide, please. So I want to basically just give an overview of the execution here. So the execution flow, it's important because what we just saw was the lowering flow. Now, once the graph that's lowered and compiled by the neuron compiler, we want to execute it. And the important thing to take into account in the execution flow is that the Amdahl's law, right? So we don't want to have any serial costs come into the end-to-end execution, because it totally spoils the end-to-end performance. The compiler does a very good job in optimizing it, but if you have some serial overheads in your execution, that totally harms the performance. So let us say if you want to iterate for one iteration, right? Your one loop of your forward backward graph. What happens is you trace the graph, you compile the graph, you load the data, and you execute it, right? So there's a lot of serialization going on here. So what the torch loader, what that does is it kind of overlaps these different phases of execution, so that when one batch is being processed end to end, you have another batch which is overlapped behind the first batch. So that way your tracing overheads can be overlapped, your compilation can be overlapped, and also the compilation also, since each iteration can be most likely the same as the previous iteration, there's a caching happening. So we retrieve from that compilation cache, and this helps in totally avoid the overhead the second time. And also please, it's not drawn to scale, so it's just different stages here. It doesn't really mean that they're the same time. So this kind of execution is very, very XLA compile, trace, just in time trace, compile, that flow. And in future, even the tracing overhead will be minimized if we switch to Torch Dynamo. Next slide, please. So what we have, this experience, our particular experiences with GPT-3 and BERT scale out. We were able to take a PyTorch XLA model and scale out to more than 16 Trainium nodes clusters. So this is our experience migrating these workflows to XLA based clusters. So for a single worker, our experience has been fairly smooth. We use Hugging Face models, and then we kind of seamlessly or almost used by replacing the device specification in the PyTorch with XLA device. We were able to smoothly convert it to XLA based code. There were some minor incompatibility issues at PyTorch API. This is mostly because, for example, if you take any CUDA like Megatron LM CUDA, it has a lot of CUDA idioms. So we had to kind of replace them or override them. And there was a lot of fused or CUDA operators. We converted them to a generic PyTorch API. And as I mentioned, we also need to use some specific XLA-centric data loaders, to overlap tracing compilation. This was a single worker experience. Now for multi-workers, we wanted to distribute them or to scale out. We encountered some gaps because the PyTorch Torch distributed API, which gives a specification of how do we insert communication operations, there was a gap coming from PyTorch to XLA. So to bridge that gap, we proposed and added a new XLA backend to the existing PyTorch API that's upstream now. So all the application has to do is instead of using the existing backends, call this new XLA backend, and you can automatically kind of pull in the PyTorch API, and you can lower it to the XLA communication API. Next slide, please. So this is our XLA backend. So what happens here is currently there are only Nickel and MPI backends, which are shown here. So what we did was we added a new backend, which one is shown as a green box. So what that does is when your application, a distributed PyTorch application, when you run it at multiple, with different on different workers or different nodes, and when you trace it, the tracing the code, it kind of hooks into this XLA backend, and when you specify that my device is XLA device, what happens is the graphs that you obtain finally, those are generated using this backend, and you can get the for example, your XLA communication operation, all those are inserted by this backend. So this helps you seamlessly. You can convert a program that was written in PyTorch with the existing backends. You can seamlessly change it into an XLA version with all the XLA communication ops inserted. So that is a new backend here. Next slide, please. And from Trainium, we have a native support. We built native support on EFA and so that you can scale to multiple topologies. Like we can create 2D, 3D mesh topologies in our network, which can support different modes of parallelism, supporting all the way from tensor pipeline to the data parallelism. And this process groups, there's direct compatibility with PyTorch API. So you can, whatever, for example, there's a new group API in PyTorch, we directly support that. The only caveat being that this kind of group API, it creates an MPMD style semantics, because what will be happening is you'll be only passing in local groups. So that kind of creates slightly different graphs across workers. So to avoid that, what we do is once you give this local topology, we can infer a global mesh. And by doing a global mesh, these slight variations are gone, and SPMD can be kind of put across the whole model, the whole application worker group. So that helps the compiler to optimize it very, very rigorously. And we are supporting distributed libraries like DDP, FSDP, DeepSpeed. It's all in works and they're already run. So we're trying to optimize them now. And FSDP is the top priority right now because it's a very nice framework which can scale out loads to multiple workers with very, very small wrapping kind of utility over the model. So any model, if you wrap it with FSDP, it can do a very good job. So that's our focus for now, but we are supporting other ones too. Next slide, please. So right now, what our plans is basically take have this a way of wrapping a model into an XLA based ops with compute communication, and then also scale them across multiple workers. That's a priority now. And our next set of priorities are very soon we want to migrate to PyTorch 2.0 with support like from Torch Dynamo, the PJRT runtime, and dynamic shapes. And we want to also start focusing on SPMD mode of semantics because as I mentioned, having a very generic utility and API to generalize, with sharding of tensors across the whole cluster, that's very important and helps the compiler too. And we also want to support more advanced models, for example, mixture of experts. I haven't listed other ones, but like stable, diffusion, all these new upcoming models. And our network is going to support, it's already there. So we're trying to support more advanced primitives, one of them being an all-to-all. So you can basically get, like, for example, a mixture of experts model with different styles of parallelism. To support that, we need an all-to-all kind of a primitive. So we're working on that as well. Yeah, so that will be all. I can, if any questions, I can discuss.
Excellent. Yes, let's do let's do strictly 5 minutes of questions so that we can cover some of the community news. It looks like many of the questions in the chat have been answered already by Shaheen. Any other questions?
So I have one question. So is this is the support code for Trainium already available to the community?
Sorry, it's released already. So you're saying that it's so you can, I mean, your question was, can you try it out, or is it?
No, I'm asking the source code of for supporting Trainium in XLA.
Yes. So if you're talking about all the models have been already, like, you know, the code of this already there, or you know, in the public domain, and the XLA backend is integrated into upstreamed into PyTorch, so you can, you know, you can get it from there, and it's all there. It's all in the, you know, public domain.
Oh, is it where the repository? So OpenXLA or TensorFlow?
So this is the PyTorch XLA for the XLA backend.
Yeah, I'm asking the backend support for Trainium.
Trainium's compiler, if that's what you're
Yes.
asking, is not open source today.
Oh, I see.
It is bounded at the XLA/HLO layer. Above that is open. Below that is currently closed.
Oh, got it.
We may change that, particularly if there's interest in the community.
Any other questions? Okay, then I think we can move on to the community news. Next slide. So just briefly, a reminder from late last year in our December meeting, we announced that Erie is moving into the OpenXLA project, which we're extremely excited about. The repo migration and community migration details are to come. We're likely going to post something in the community to gather feedback and also eventually provide the specific plan for that. We also have some open RFCs. So Jacques, do you want to take the first one, PGRT plugin?
Sure. So yeah, this is an RFC to basically, so PGRT is a way for frameworks to integrate like a package compiler runtime solution, and this is the approach we want to propose as the way of integrating like OpenXLA and OpenXLA's components into ML frameworks. And so we have the RFC. I think I posted it last night. So please leave comments here. Look at what it looks like. We have a lot of the PGRT is being used in a couple of different places, and we'll have quite a few discussions there.
Great. We have another RFC that's been posted on handling XLA exceptions in Python. So please do take a look at that and contribute if it's relevant to you. The project governance proposal, Taya, do you want to briefly touch on that? Oh, Taya's actually on mute. So I'll just briefly review the main points. Is that we're going to be merging this this week. And the main points of feedback in the RFC so far have been defining the scope of governance in terms of what falls under the umbrella of governance. And so please do leave any further comments in that proposal.